Micro Nano Education for everyone.
I'm Matt Pleil. I'm at the University of New Mexico in Albuquerque, New Mexico, and we've got a clean room. So we want to use a clean room to teach students about microfabrication and microsystems fabrication. That's kind of my thing. And I'm going to go through some slides real quick. And, I encourage you to come out and come to our 1 week thing in the summer. You'll learn a lot and get a lot of basic stuff. There's some prep work you do online before you come. And then you can do a poster in one of the poster sessions at MNT-EC, or maybe we'll take a few students to high tech to do a poster, and there's money involved. So, and the mentors that are on the line, if you have students that want to come, you can come with your students. I have money for professional development as well. And then Jared and I will fight over who's going to pay for what. So we'll get you out here. Okay. So consider doing that. It's a lot of fun to do it, faculty with their students. That's kind of what I encourage. That's my thing. So let's talk about what microsystems are and why they're important. So microsystems are the little widgets inside your phone and inside your car that convert environmental information into an electrical signal. Those are called sensors. And then you also have actuators, right? So you send an electrical signal and something moves. So that's why we call these microsystems, we also call them micro electromechanical systems. So most of this stuff's on the order of microns. We do thin film deposition, which is on the order of nanometers. So we do play in the nano realm as well. And microsystems are used to enable us to do things on the nanoscale. So atomic force microscopes use a microcantilever, for example. So if you learn about AFMs in your classes, the way those work is through a microcantilever. The image you see on the right there is a chain that one of my technician students designed back in 2006, and it was made at Sandia National Laboratories. And each chain link is 10 microns. So human hair is on the order of 80 to 100 microns. So about 10 chain links there would go across the diameter of a hair to give you an idea of the scale of things. And microsystems are made in clean rooms, just like a lot of nanotechnology is done in clean rooms. So the things you learn when you come out to our site is totally applicable to nanotechnology as well. There's a lot of overlap, in other words. So I'm sure you guys know about scale, nano, micro, and all of that. I deal with the middle pretty much in the work we do. And there's a close-up of a Sandia National Labs gear, and each gear tooth is 8 microns. And to give you an idea, if you were to take a red blood cell, it would drape over the gear tooth. So they're pretty small. And the type of MEMS devices that are out there, you've got micro sensors and actuators. So we've got 3 and 6 axis accelerometers that are common in cars and phones. Anything that you're tracking that has motion associated with it will have usually a 6-axis accelerometer in it. Lab on a chip, we used a lot of that stuff for COVID testing, for example, but also a ton of other applications. They include microfluidic channels, and you can see a scanning electron microscope picture there on the upper right, showing the microfluidic channels. And so you can make things like that. On the bottom right is a design image of a digital mirror device, and you'll see an actual picture one later. These are used in all the theaters that you go to now. So it's based on digital information. The digital information is converted into motion on individual mirrors, and you'll have 12 million mirrors per chip and 3 chips per projector, and you get super high resolution, very good contrast ratio, and all of that. And so when you go to the theater, what you see on the screen is based on a MEMS device. And of course, there's a lot of biological applications. One of the more useful ones is the pacemaker, and pacemakers have a bunch of sensors embedded in them to help the pacemaker make decisions as to how fast to make your heart go, okay, based on activity and motion. So we find MEMS in automotive systems, okay, consumer products, cell phones, tablets, wearables, Garmins. The Internet of Things is integrating all of our electronics and sensing systems into the internet. And so we need sensors to gather information and put it out as a voltage. Once you get it into a voltage, you can do processing on it with logic and computer chips, and then turn it into real useful data. And that data is ported into the internet. And so you can see what temperature, your house is at on your phone app, for example, if you have one of those, fancy thermostats and whatnot. You can turn on lights on and off through your phone app. And a lot of that is based on either computer chips and or Microsystems MEMS devices, okay? The market is huge. That's why you might want to be interested in a career in this area. This shows you a bunch of different types of devices that are used out in the real world. So you have surface acoustic waves, optical sensors, fingerprint sensors, gas sensors, magnetic sensors, whatnot. And these are just for sensors. Okay, so you can see that we've got a compounded annual growth rate of 10 to 15% per year. That means more money, right? That's based on money, not number of chips or anything like that. It's all on money. So if your industry is growing at 10% per year in revenue, that generally means the jobs are opening up at a similar rate. Okay, so the future is bright. And you may have heard on TV recently about the semiconductor boom in the United States. I know Intel is investing in Ohio, $20 billion. They're also investing in Arizona, $10 billion, and in New Mexico, another $5 billion to expand the current factory we have in New Mexico. Taiwan Semiconductor is building a $20 billion fab in Arizona. And there's a ton of expansions going on all across the country. So there's a lot of technician jobs, engineering jobs out there. So the future is really bright for people who understand the basics of this. And quite frankly, if you have a basic understanding where you know what a wafer is and you understand the basics of lithography and etching and thin film deposition, which you'll learn if you come to our workshop in the summer, and you've learned it and you can talk about it and show them the gadgets you made in our clean room, you'll probably get the job. So here's another cartoon of showing compounded annual growth rate for the different sectors within Microsystems. So you can see, pressure sensors is a fairly big circle, and you're going to learn how to make those. RF MEMS is more on the radio frequency side and communication side, and those are growing at a really high rate. So, everything is exploding. Nothing is contracting. So the future is real bright. And this shows you how the hardware and the data stuff goes together along with cloud storage and whatnot. So you need the hardware to access, the information and to gather information environmentally. So that's where the sensors come in and the clean room devices and clean room made devices come in. And then the data are the coders and the guys who actually do the code so they can make sense of the data. And then the cloud side is, everything's stored on the cloud. So you need more servers and storage capacity for cloud computing and all that. So there's tons of jobs in all of these areas. So whatever's interesting to you, you'll find something that you'll like. Okay, and here's a little cartoon of some of the sensors in a cell phone. So you can see a list there of everything in a cell phone that's related to Microsystems and MEMS. On the upper right, you can see you can buy an add-on to your phone that turns it into a FLIR camera, and FLIR stands for forward-looking infrared. So you can turn your phone into an infrared camera with a small attachment. Usually it's about $200 or so. And then on the bottom right, you can see a cell phone that has a built-in digital mirror device projecting system. So you can actually project videos from your phone. So you can buy these phones as well. Or you can connect your phone to a Pico projector, which is like the size of, I think a matchbox or so. So, miniaturization is taking over, and it's driven by MEMS technology. So that's a few things there. And then here's a cartoon showing you some of the different sensors inside of smartphones. So there's environmental sensors now that Bosch is coming out with. So your phone will tell you if you're in an unsafe environment, maybe carbon monoxide is too high, or, there's some volatile gases or something like that. So, pretty soon, you'll have that capability on your phone as well. And I wanted to pitch a little bit Texas Instruments. I used to work there back in the day. And in 2015, Larry Hornbeck, the inventor of the digital mirror device, got an Oscar, which is an Academy Award of Merit for technology he developed. Since all of the different theaters now use digital mirror devices and digital projection systems, and all the films are being recorded digitally as well. This technology was what made it possible to do that. So, and Star Wars, when they first started Star Wars, they actually wanted to do most of it digitally, and they were told no because we had all film-based theaters in the United States. So they had to do it in film. And then later on, they did it both in film and digital. And eventually it all moved to digital. Okay. So we've had lots of students come out and faculty over the years to our clean room. Here's a snapshot of one of our clean room activities a few years back. And it's a lot of fun. You can see that everybody's smiling behind their masks. So we encourage you to come out. There's a picture of our building. So when you first come and you see this building, that's the one you go into. Okay. And we have lots of different topics we can cover as part of the URE experience. Usually if you're a first timer, you come out, you do a few activities in the clean room and make a pressure sensor. And then if you want to delve into something specific, you have a day or two to do some characterization work and whatnot. If you want to stay a second week, then we can do more depth into a topic, because then you'll know how to use the equipment and how things work, and you can do more stuff on your own. Okay. And then at the end of everything you learn in the clean room and stuff, you can do a poster. We highly encourage that, both Jared and I. And if you create a poster, you can present it in the virtual poster session as part of the MNT-EC conference in July. Okay. And we'll at least SCME will give you an extra $500 for doing a poster, and we'll send you an Oculus 2 headset. So I think everybody from Jared's group did a poster last year. That was a lot of fun. So we're going to do the same thing this year. And I think we're going to select a few students and take them to high tech for posters as well. So that's another thing you can do. And if you go to the MNT-EC website down here, and Jared can share that link with you as well in the chat box, you can look at the posters and walk around in virtual space if you want. Okay, so when you first come to our clean room experience, you're going to be in the fab. You're going to make what we call an art wafer. So here are some examples from students making art wafers. And on the upper right is an example of what an art wafer is. So you're going to create a design, and then you're going to send it to me, and then I'm going to print it out on a plastic sheet. And when you come here, the first day, you're going to make your art wafer. So that'll allow you to learn about photolithography and wet etching, okay, in a day. So that's a lot of fun. And then the second day, we start making our pressure sensors. Okay, so you can see what the final pressure sensor looks like from the front and the back of the wafer. Okay, it's basically a Wheatstone Bridge circuit on top of a membrane that can flex. And when the membrane flexes, it stretches the resistors on the Wheatstone Bridge, changes the voltage output, and you can compare voltage with pressure change, and now you have a calibrated sensor. And the bottom right inset picture is from the top of the Wheatstone Bridge, showing you the probes that we use to electrically probe it to get that data out of the chip. And then the pressure sensors are found in a lot of different places, but one of the most common ones that you might be familiar with is inside of your car tire. So you know when you need to add pressure to your tire. They're also in your phone. That's so you can do internal navigation in buildings, because the air pressure changes as you move in altitude. So if you have a smart application that can look at that data, it can calculate how much distance you went vertically. So it's for internal building navigation, also for first responders to locate people if they call from inside of a building, have a heart attack or something, and they got to go find them. They know what altitude they're at as well as what XY coordinate they are at. So some homework for you guys if you're interested in this. You can look up an app called Sensor Kinetics and download it onto your phone. So you might want to write down Sensor Kinetics. And it's free. If you pay the, I don't know, $6 or whatever for the pro version, you can actually store your data, save your data, and then analyze it offline. But what Sensor Kinetics does is it allows you to look at the individual sensors in your phone and see what the voltage output is from those sensors. Okay, so you can get a lot of cool data on that. So I like to use that. You know, I can measure the height of a table using the pressure difference that I measure with my phone, which is kind of cool. And that's what the homework is. So in this example, I actually measured the height of a table to be 2.4 feet, looking at the difference in pressure. And then I used a tape measure, which is a lot easier, and it was 2.5 feet. So, you know, it's a pretty good thing. But if you're like hiking and you want to know how much height you went, you can use this pressure difference as well, just to see, you know, it's kind of fun. So we do the pressure sensor process. It takes about 3 days to get the process done, and then we do some characterization work at the end of the week. We also do some microfluidic stuff. So we'll make microneedles and microfluidic channels as well while you're out here, if you're interested more on the bio side. Okay, there's another picture of the Wheatstone Bridge actually in a package. So you'll get to take your Wheatstone Bridges back with you, and you can design your own package if you want and further your learning. Here's some of the tools we use in the clean room. So on the left side is our sputter tool. Sputter allows you to put thin films of metal and other materials onto the wafer. And then on the right side is an oxide furnace where we actually grow the silicon dioxide on the wafer. For example, we use that in the art wafer process. Okay, these are our lithography tools. So we have code, expose, develop, and rinse. So you'll get to use all of these tools yourself. We don't do a show and tell where you watch us use the tools. We actually have you do your own wafers. Takes longer, but it's more fun. And then here's an example of our two of our dry etching tools. We have a March reactive ion etcher on the left, and then on the right is a deep reactive ion etcher. And the scanning electron microscope picture on the top left is taken from the deep reactive ion etching. So you can see we can make really tall, skinny things with the deep reactive ion etcher. And here's a picture of our probe station. You'll also get to use that if you come out. And on the upper right is an image from the microscope showing the interference pattern. As you change the pressure on the membrane, it flexes up and down. And then you can get an interference pattern and determine how much it flexes in the z-axis. We have a scanning electron microscope you'll be able to use, and a profilometer, and a probe station we already mentioned. And so you can use those metrology tools to measure other things as you go through the processes. On the right, there is a digital mirror device, then actual scanning electron microscope picture of it. So we have several of these devices deprocessed, so we can put those into the scanning electron microscope so you can see it. And I just want to acknowledge my partner, Dr. Nathan Jackson. He's an expert in MEMS and MEMS devices and applications, and he's done a lot of bio stuff. He's actually a bioengineer, but works in the mechanical engineering department. And then on the right, you see Pallavi Sharma. She's one of the 2 grad students that will be working with you. And she's a PhD student, and she should be finishing her PhD this summer. And she's already looking for jobs, but she's an expert on all the equipment in our clean room. So that's all I have. So if we have time for questions on anything.
I have a question.
Okay.
I saw in the presentation there that MEMS can be used when it comes to chemical and drug delivery. Now, is it possible for that delivery to cross the blood-brain barrier?
Yeah, you could put, like, there was a guy years ago at UNM, he was making neural probes. So there was a really interesting device he was making, and I think they only used them on rats, because they were developing it. But the device had an ultrasonic imaging system built into it, as well as microfluidic pumps and channels. So they could put the device into the brain. They could image what's going around on a very small scale with the ultrasonic transducers. And then they could introduce chemicals, drugs, whatever, and see if there was a change in the brain. But on a very small volume, right? It was made to do very, very specific small things. And then other people have made probes that they could move up and down in the brain and then and sense electrical signals. So you could combine those 2 things if you wanted to, right? And make a probe that you deliver some drugs and look at a change in the electrical signals. Yeah, and I saw either a documentary or video where a guy had Parkinson's and he had the tremors really bad, and then they would turn on some electrical signals, and I think they had probes in his brain, and it would stop the tremors. It was like turning on a light switch. That would be something worth looking into, right? Because
for sure.
All right, cool. Thanks, Matt.